I'm Chin-San, number AN200206. The title for my project is The Investigation of Vehicle Performance and Exhaust Emissions under Low Load Conditions. Biodiesel is a process fuel for diesel engine vehicles. It can be derived from vegetable oils such as plum, coconuts, or it can derive from animal fats. Biodiesel refers to 100% of biodiesel fuel. A standard diesel vehicle engines can only run on pure biodiesels when there are modifications to the engines, because pure biodiesels will condense during the cold temperatures and it can corrode the seals in older diesel vehicles. Therefore, the fuel used in engine is the biodiesel blends such as B10 Palm Oil Biodiesel blends, where 10% of palm oil biodiesel is blended with 90% of diesel, pure diesel. So the advantage of biodiesel are portability, renewable, higher combustion efficiency, and reduce the sulfur emissions. The disadvantage for the use of biodiesel has higher viscosity. It will produce higher nitrogen oxide (NOx) emissions, cause injector choking, and engine wear due to engine corrosion. The research objective is to investigate the performance and exhaust emissions by using B10 Palm Oil Biodiesel blends under low load conditions. The problem statement is in this report have two. First one is engine dynamometer result cannot reflect the real world performance. That's why we need to do the chassis dynamometer experiments. Next, they do not have specific B10 Palm Oil Biodiesel blends engine research under low load condition. So the scope in this project, first one is using the Unitech chassis dynamometers, and the experiment is run under low load conditions where the RPM is set 1200 to 2200 RPM. The fuel used is B10 Palm Oil Biodiesel, and the vehicle used is Mazda CX-5 with SkyActiv-D technologies. The significance of study, first is the performance. Engine performance for B10 Palm Oil Biodiesel blends under low load conditions can be studied, such as brake power, brake torque, BMAP, and VFSC. The exhaust emission for B10 Palm Oil Biodiesel blends can be investigated, such as carbon monoxide, carbon dioxide, hydrocarbon, and nitrogen oxide. So here are some subtopics that I study in Chapter 2, Literature Review. For the fuel type, I had studied the fuel properties such as heating value, Cetane number, viscosity, density, sulfur contents, and flush point for both fuel, that is pure diesel, which also act as benchmarking in this experiment, and the other one is palm oil biodiesel fuel properties. So I also study some of different technologies in diesel engines, and first one is CRDI engines. So in the study, IMAP will due to fuel injection pressure increase. Next, average reduction of 2.43% in BFFC, and finally the brake thermal efficiency BTE will increase due to higher compression ratio and injection pressure. Next is TDI engines. Low LHV of biodiesel will increase the BFFC of the engines, and total particle number concentration will decreases, which about 38% reduction in the size range of 5.6 to 560 nanometers. Like duty diesel technologies, the higher viscosity of biodiesel will reduce the fuel injection angle and available air in the fuel injection area, which will reduce the carbon dioxide emissions. So I also study some different conditions. First one is the speed. When the engine speed is increases, the brake power, brake thermal efficiency, and brake torque will increase too. The higher emission of hydrocarbon and nitrogen oxide are at the lower speeds for all biodiesel blends. For the load conditions, the high loads will increase in air-fuel equivalence ratio, result in an excess of oxygen, leading to more complete combustion and an improvement in engine output power. So under low engine loads, the SFC values for biodiesel mixtures are lower than those of pure diesel fuel. So the emission of carbon monoxide will shows a decreasing trend from 0 to 75%. Finally, I've studied the SkyActiv-D technologies. It has the lowest compression ratios, which is 14 to 1, and it has 20 to 30% better fuel efficiency. SkyActiv-D do not use the expensive NOx after treatment system. It has a new two-stage turbocharger for smooth and linear response. Precise injection quantity and timing increase the accuracy of mixture concentration control and ensure the cool start capability. Here are some reference that with title, authors, findings, and summary. So for the chapter 3, methodologies, first one is fuel. The fuel that I use in this experiment is Biodiesel Max Euro 5 because it has some advantage such as it can improve the fuel economy, reduce the exhaust emissions, improve oxidation stability, excellent corrosion protection, and finally it has cool start performance. In this table, the fuel properties for Biodiesel Max Euro 5 are shown. Biodiesel Max Euro 5 is B10 Palm Oil Biodiesel. So vehicle used in this experiment is Mazda CX-5 2.2D High Plus. It has 2,191 cubic centimeters cc, compression ratio of 14.4 to 1. Maximum power it can produce is 188 horsepower at 4,500 rpm, and maximum torque it can produce is 450 nanometers at 2,000 rpm. The table shows some another specification for the vehicle. Next, the chassis dynamometer that we use is all-wheel drive 150 model with a K140 model eddy current power absorber. The maximum load capacity for the chassis dynamometer is 625 horsepower. The power measurement is about 2,000 horsepower. It has synchronized front and rear rollers, and it also has the exhaust gas analyzer that we can use to measure the exhaust emission. So to run the experiment, I have divided into two stages. First one is before experiments. So all the components at the chassis dynamometer must make sure in good conditions to avoid any accident happens. Next, the condition for the vehicle such as tire pressure, engine and transmission oil, plug belts and hose must be checked. all the tools are enough and functioning. And finally, the self-safety is needed, such as wearing earplug and safety shoes. After done all the checklist, CX-8 now can park on the dynamometer. So during experiments, two people are needed. One is to operate the vehicles and another one is to take the result. So the engine speeds are set from 1200 RPM to 2200 RPM. So first, the vehicle engine speed is set to 1200 RPM. After it is constant, the result for the brake torque, brake power, Bmap and BSFC is recorded. The oxygen sensor was inserted to the exhaust pipe and the data was recorded by pressing the gas analyzer button. So the data need to collect carbon dioxide, carbon monoxide, hydrocarbon, and nitrogen oxide. The experiment were repeated by changing the engine speed as shown in the slide. So this is the flowchart to run the experiment. So first, we need to have a data gathering. This is the previous research about our experiments. Next, we need to set up the chassis dynamometer. After we make sure all the condition is good, so we can proceed to run the experiment with low conditions. Next, we'll make sure the result that we take is reliable to the research that we have made. So after that, the experiment is done. For the chapter 4 expected result, so the brake power were expected to be slightly lower compared to the biodiesel. The torque output were similar or slightly lower than pure diesel under low load conditions. The fuel consumption expected to be slightly higher compared to the pure diesel. For the exhaust emission, the result expected were slightly higher than pure diesel. So the B10 Palm Oil Biodiesel blends are expected to result in lower carbon monoxide and hydrocarbon emission under low load conditions due to the emission control technologies in the SkyActiv-D engines, because it will improve the combustion efficiency of the biodiesel. Finally, the SkyActiv-D engine's design and management system can influence the outcome that are different from previous research due to it has the specific characteristic and technologies. And lastly, this is the Gantt chart for my report. So the date shown is the started date to the end date for the task. So that's all from me. Thank you.